In this talk, we're going to examine the topic of electromagnetics and some of the fundamental aspects of electromagnetics necessary today to understand today's world. Electromagnetism is one of the four fundamental forces in nature. The other forces are the nuclear forces, the weak and the strong nuclear forces, as well as gravitational force. So electromagnetics as a subject is often broken down into pieces based on whether it's a static field or dynamic field. So there's a field called electrostatics that looks at the static properties of electric fields, magnetostatics, which looks at the static properties of magnetic fields, and then the field of electromagnetics combines the two into a dynamic form. So when you have a changing electric field, you actually can generate a changing magnetic field, and vice versa. So as the changes happen, you actually generate a self-propagating field. Some interesting properties about the electromagnetic field is that it propagates in an empty space, so in a vacuum. Unlike a wave in water, it doesn't require a medium such as water, or a sound wave in air requires the air to propagate. Electromagnetics do not require any of these physical substances to propagate. The propagation of the speed of light is constant in the vacuum. It does vary as you enter into different media. So in a water or versus air versus inside a block of wood, the electromagnetic wave will propagate at different speeds. One interesting application of the electromagnetic wave, a natural application, is the Earth generates a magnetostatic field. So there is a magnetic field around the Earth, and that field manages to protect us from high energy particles that are generated in the sun. So the magnetic field actually operates on charged fields because they are generating magnetic fields, and this results in what's called the aurora borealis. We are all familiar with the electromagnetic spectrum, whether we use radio waves or microwave ovens or just through our visual capabilities from eyes. Starting from the far right in the electromagnetic spectrum, according to the plot shown, we start out in quasi-static fields. So moving beyond the static fields of electrostatics and magnetostatics, we first encounter things like transmission lines and power systems that generate changing magnetic fields and changing electric fields, although those changes are over a very long period. Next, we move into the radio waves, and as you can see by the scale on the graph, you're talking hundreds of meters to meter-long waves, so fairly large wavelengths. Next, you move into the microwave region, which is not only for your oven, but it's also where radar systems operate. Most communication systems will use carrier wavelengths in the microwave region until you move into fiber optics. So the microwave region is a very important region. Somewhere between the microwave region and the infrared region, in that gap between those two, you find terahertz, which is where a lot of imaging systems now work. You also find some radar systems moving up into the millimeter waves. So there is a new region of operation between microwave and infrared. So infrared is the next region that we encounter, and the infrared region is where we have a lot of radiation from hot bodies. So a lot of the sun's energy comes to us through infrared radiation. The next region from infrared to visible is where you find your night vision goggles. So somewhere in the near infrared region is night vision. The visible region, which we are all the most familiar with, this is where our optics are encountered. So we go from red to violet light. Next after that is the ionizing radiation portion of the electromagnetic spectrum, ultraviolet, X-rays, and gamma rays. And we've heard of these, but we may not associate these with the electromagnetic spectrum. And these are high energy waves, and in some cases, ionizing radiation means that it actually can do some damage with longer exposures. Nature's electromagnetics shows up in multiple ways. Some phenomena that you can see in nature include, from these pictures, you see that we have mirages. So that's the bending of light based on a differential in thermal properties of the air. So the index of refraction of the air is just such that it bends the light from the sky at the surface of the road. So you're actually seeing a reflection of the sky in the road. Lightning's an electromagnetic phenomena. It moves from the electrostatics into the electromagnetics. Rainbows, the aurora borealis already mentioned, as well as the body itself generates electromagnetic fields, and these fields are exploited in things like the electrocardiogram or electroencephalograms and magnetoencephalograms and several other medical imaging techniques. So there are plenty of applications from radio astronomy that take advantage of nature's electromagnetics. The technology around us gives us more exposure to electromagnetics. Most of the systems that we're accustomed to, everything from entertainment to power systems to communication systems and radar systems, even some even more familiar systems such as your cell phone, are all based on the use of electromagnetics in one way or another. So who uses electromagnetics? Well, again, this is kind of rehashing, but nature uses electromagnetics through your eyesight, lightning, astronomy, power systems, generation, transmission, and distribution all use electromagnetics to both generate the power itself as well as transmit the power. Wired communications, guided waves, cable, TV, fiber optics, wireless communications, so cell phones, satellites, radio, GPS, are all using electromagnetic phenomena to get you information. Radar systems, mapping systems, weather, automobiles, so forth. Biomedical imaging systems, so MRIs, CTs, so computer tomography, so we have optical coherence tomography, electrocardiograms, magnetocardiograms, and many others, like I mentioned, electroencephalograms. Entertainment, so TVs are broadcasting the information from the TV screen through a electromagnetic phenomenon known as light. The Blu-ray player uses a laser to read the surface of the discs. Computer graphics actually use electromagnetics not only to display an image to you, but also to create that image. So they mimic ray tracing, which is often used in electromagnetics to simulate a scene. The electric field is created by separated charges. A simple example of that would be a separated positive and negative charge, as shown to the right. So we see a positive charge and a negative charge, and those lines between them are a representation of what that field looks like. These fields can attract and repel, so they can exert force on charged particles. So it's not just these two charged particles with a attractive quality, but if we bring in another positive charge, it would be repelled by the positive charge and attracted by the negative charge. So we actually get a amount of work done. The magnetic field is generated by, or the magnetostatic field is generated by charges in steady motion. So current flowing in a wire in a certain time frame will be relatively constant and will generate a magnetic field. The magnetic fields also, just like the electric fields, can attract and repel. So two wires close together with the right properties, with the right direction of current flow, can actually pull towards each other. Now we're going to talk about electromagnetic waves. Electromagnetic waves are created by accelerating charges, and typically if we're talking about a man-made device, those accelerating charges are on antennas. So the electromagnetic wave can travel through empty space, in other words, a vacuum, versus mechanical waves, which require a medium in between. So the relationship between the frequency, the speed, and the wavelength of a wave, an electromagnetic wave, is the frequency times the wavelength equals the speed. So they're all interrelated. The only constant is the frequency inside a medium. So if light enters, or if an electromagnetic wave enters from one medium to another, the frequency will remain constant, but the wavelength and the speed will change. The frequency of an electromagnetic wave determines its propagation characteristics through various media. So a lot of the characteristics that we will not go through, but are an important part of the electrical engineering side of electromagnetics, are dielectric properties and magnetic properties of the materials themselves. Waves spread out in space, so they spread typically with a spherical wavefront. So that means, like you're blowing up a balloon, the surface area keeps increasing, but the amount of material or the thickness of the wall of the balloon actually is decreasing. Likewise, as the electromagnetic wave spreads as a spherical wave, the power density at each unit area is decreasing. So wave interaction with a wall, and here we're talking more or less about plane waves, which are not within the scope of this discussion. So in a wave traveling from one medium to medium 2, which is a finite slab, to medium 3, you actually have several different phenomena taking place. You have incident energy, so the electromagnetic encounters the medium. At the interface between the media, you actually get a reflected wave, and a transmitted wave. So the wave that is transmitted into medium 2 is not only absorbed by medium 2, since all real media are lossy, but it's also reflected at both the original interface on the left side of the medium slab and at the interface to medium 3, so the interface between medium 2 and medium 3. And finally, after you account for all these different energy reflection and absorption mechanisms, you get the transmitted energy. So this interaction, however, must obey the conservation of energy. So in this slide, we're going to talk about 3 phenomena that are of interest in many man-made devices: the absorption, transmission, and reflection of electromagnetic waves. In each case, the conservation of energy must be applied and the conservation of energy must be obeyed. So the energy in is going to be equal to the energy out, which in this case we're going to consider the transmitted energy, plus the reflected energy, plus the energy absorbed. The reflection takes place at all the interfaces between separate media. The angle of reflection, as you may already know, is equal to the angle of incidence as measured by a direction perpendicular to the surface of the media interface. Transmission is the energy that makes it through the obstacle. So after it makes it through the interfaces and is reflected and is absorbed by the medium, this is the energy that emerges on the side where you're trying to make it come through. So if it's a cell phone signal trying to get through a wall of a building, then the incident energy is the energy in the atmosphere that makes it to the wall of the building. The energy travels through the wall. Some of the energy is reflected off that wall. Some of the energy is transmitted into the wall and is absorbed by the wall. And some of that energy actually makes it back out into the rooms inside the building. So this is the transmitted energy that we're mostly interested in. In most cases, refraction will take place, and sometimes it may not be observable refraction just because the angles can be very small. But whenever a wave crosses the boundary of 2 different media, the direction of the wave is changed to a degree. And these depend on the material properties. Absorption in a material is another material property that converts the electromagnetic energy into a different form of energy. So in most cases, that's going to be heat. So electromagnetic wave will heat up a material. And this is more or less the principle that we're talking about with microwave ovens. So energy absorption can take place upon reflection or in transmission. So radio wave propagation effects are what we're most interested in cell phone communications. So the signal to and from your cell phone, if you look at the tower illustrated to the right, you'll see that we have a tower that's broadcasting. There's a direct signal that reaches the car where your cell phone is resident. So the direct signal is the most desired signal. Other signals can actually reduce your data rates. So there's other ways to get reflected signals. Some of them may be reflected off other buildings. Some of them may be diffracted signals, which are radio paths that go around obstacles to some degree. And waves can actually bend into regions that appear to be quote unquote shadowed by a building, for example. Scattering, it takes place on a smaller wavelength scale than reflection. So if there's fog in the atmosphere or something like that, that's often considered scattering rather than reflection. So your cell phone is probably a 4G cell phone, which means it operates up to about 2.5 gigahertz. But we're going to do an experiment where we're going to look at higher frequencies. So we have a device that will generate microwave frequencies from 10 gigahertz to 16 gigahertz. In this case, it actually does a lot more. And what we're going to do is generate a signal, and we're going to transmit from a horn antenna on the left through a panel or through free space to a horn antenna on the right. So since the device we're using can measure the relative signal strength And the device is called a network analyzer. It's in the center of the picture there. So it measures the relative signal strength from the transmitted to the received. So, and it measures that as a ratio. So it sends a signal to the antenna on the left, and it receives a signal in the antenna on the right, and all these are translated back to the device. So if you look at the trace of the signal, we actually see it's at negative 30 decibels. So the ratio between the transmitted and the received signal is negative 30 decibels, which means it's loss. So it's got a ratio of 1 to 1,000. So 1/1000th of the power is received. Decibels are used because when you get ratios of 1,000 to 1, the signal levels create a graph that's very large. So you want to compress that, and so we use the decibel system, which is a logarithmic system that's used in audio systems like your stereo and so forth. But we also use it in electromagnetic signal strength measurements because it's convenient to show things as large differences. So again, we see a negative 30 decibel level signal is received relative to what was transmitted. So at 13 gigahertz, we actually have a marker there that shows that we received negative 29 decibels. So first thing we're going to do is normalize that system so that through free space, we're going to set that signal level at 0 decibels. So we're going to say, okay, we have a signal that's transmitted, so anything now that introduces loss into the system beyond what's lost in free space will show up as a negative number. So we've rescaled to plus or minus 10 decibels, and now we're going to try inserting a metal plate in between because metal shields electromagnetic signals that will reflect off. It'll go off into the room. So first thing we're going to do is we're going to put that 2 by 2 foot piece of aluminum in between the two antennas, and we're going to see that the signal strength has dropped down to negative 45, negative 50 dB or decibels. At negative 50 decibels, you're looking at a factor of 1 to 100,000. So it's 1/100,000th of the signal strength. So most of the signal has been blocked by the metal shield. So the next thing we're going to do is look at cinder blocks. Cinder blocks are a common building material. You might see them in institutional buildings like at Virginia Tech, and you also see them in your basement, maybe at home. So if we put one cinder block down, you can see it does not block the signal directly between the two horns. So we need to add a second cinder block, and you see the signal drops again to negative 26 decibels. So negative 26 decibels is about half of what we saw on the decibel scale for the metal plate versus cinder blocks. So cinder blocks do block signals. It's not as good as metal, but they will block the signal, which explains why you may see cell phone drop in your basement or in some buildings where there's not enough windows. Typically, you'll also see in these demonstrations that we have a lot of noise on our signal. That noise is due to the fact that we're not operating what's called an anechoic chamber. An anechoic chamber, you see all these blue pyramids. This absorbs all the reflections that go around that generate a lot of the noise that we're seeing. Polarization is another property of electromagnetic waves. Waves are polarized by the preferential alignment of the electric field as it propagates and interacts with matter. So the polarization can become very important in the way the electromagnetic fields interact with the matter. If the wave oscillates more or less up and down, for example, if you consider an XYZ coordinate system or a Cartesian coordinate system, and the wave oscillates in a linear fashion within that coordinate system, then it's typically called a linear polarized wave. In other cases, the electric field can actually trace out a circular path, so it's kind of like a corkscrew as it travels through the atmosphere. And if you project that onto a plane, it looks more like a circle, so it's circularly polarized. And finally, the most general form is when it's elliptically polarized. So the electric field kind of does the same corkscrew, but has a slight variation from one axis to the other. The electromagnetic field is polarized according to the direction of the electric field. The electric field, in this case indicated in red, is directed along the x-axis, and the magnetic field indicated in blue is directed along the y-axis. The antenna itself is also polarized. In this case, we're calling this vertically polarized, so the electric field is in the vertical direction in the antenna's case. So if we introduce a polarization grid where wires are also oriented in the vertical direction, the electric field will push electrons along those wires and actually re-radiate the field back at the horn antenna that's transmitting. So we'll actually get a reflected field back, and we'll have some transmission loss as a result. So if we look at our measurement system, if we look at a free space transmission at 0 dB, everything that's going to be lost is due to the polarization grid's introduction. So when we put the polarization grid into the system, we see an immediate drop to about 6 dB of loss, which is 25% of the power. Now, if we rotate the polarization grid so that the wires are horizontally polarized, so they are cross-polarized with the vertical horn antennas, so the electric field and the wires no longer line up, we end up with a situation where the electromagnetic field is not going to reflect back. So as we rotate the polarization grid to its horizontal position, so the wires are now cross-polarized with the vertically polarized incident electric field, we get full transmission, or nearly full transmission. There is one unique phenomena that can occur in the reflection of electromagnetic waves. So as waves are reflected from surfaces, depending on the geometry of the surface, the relative polarization of the electromagnetic wave to the surface itself. As we saw before, we had a perpendicular line from the surface that determined the angle of reflection. Well, in the same way, the polarization can vary with the angle of incidence. So if we consider two different polarizations, one which is perpendicular to what's called the plane of incidence and one which is parallel to the plane of incidence, in the figure on the bottom left, it kind of gives you a hint of what that means. So we have an electric field E with a parallel symbol and E with a perpendicular symbol. So those are two waves with two different polarizations. So it turns out that the wave with the parallel polarization can actually create a situation in which all the power can be transferred and none reflected at a fairly high angle of incidence. So if you look at the plot up to the top in the right-hand corner, you see the two traces of the different polarizations and their reflection coefficients. So the magnitude of the reflection coefficients. At 0 incidence angle, so straight onto the surface, directly, incident on the surface, looking down, for instance, these polarizations meet. They both are around 0.19 in this particular figure. Now, if we look at how the polarizations diverge, however, the parallel polarization, which is the orange line, goes down to 0 and then back up to 1 at 90 degrees incidence angle, whereas the perpendicular polarization just gradually turns up, so it's monotonically increasing towards a reflection value of 1. And keep in mind, this is an absolute value of the reflection coefficient. So in everyday's experience, one of the ways you can think about this is looking with a polarized lens. So through a standard lens with no polarization preference, you get a lot of reflection off the surface and you can't see what's underneath the surface of the water. But if you put it through a polarized lens where you filter out the wave polarization that's always reflected positively, so the perpendicular polarization, and you only look at the parallel polarization, you'll see in the graph that parallel polarization is 0.19 or less all the way up to 65 degrees or so of incidence angle, and it's even 0 at 55 degrees incidence angle. So at 55 degrees, roughly all the power is transmitted through the surface of the ocean and encounters the bottom of the ocean and is reflected off of those features in the bottom of the ocean and comes back up to the surface, and that's what you can see. So that allows you to actually see inside the surface of the water, whereas if you don't filter out that perpendicular polarized component, all you see is the figure to the left, or the photo to the left, where you're getting a lot of reflection off the surface of the water. So this phenomenon can be used for a lot of different applications in electromagnetics to enhance the ability to penetrate walls and so forth using electromagnetics. So if you design your polarization to match the geometry of your situation, you can actually transmit more power if you consider your methods so that you produce a parallel polarization. Finally, what are the careers in electromagnetics? Well, some of them are more subtly electromagnetics than others. Some are more definitively electromagnetics. In communication systems, for example, There's a lot of people that do antenna design. They look at the radio system overall, so they look at propagation environment. So how does a wave propagate through a city, for instance, or in the mountains? So this explains why you see your cell service drop. So the people that work in this area do their best to get full coverage with as few cell towers as possible. In radar systems, you also see a lot of people working in antennas. Remote sensing deals with how the waves scatter off the surface, whether it be airborne remote sensing or spaceborne remote sensing. Weather radar is another big area. How does the electromagnetic wave interact with different kinds of weather? Can it see raindrops? Can it see snow? Can it discern between the difference between snow and rain? Can it find other weather phenomena that are important for air traffic, for example, like microbursts? In automobile radar, the wave interaction with other cars, the wave interaction with the road and so forth helps keep you safe with automatic braking and is going to be a major component of self-driving cars. Sensor systems, which overlap with radar systems, but more generally, include proximity sensors, medical sensors, flow, fill, motion. There's all kinds of sensors that use the ability of the electromagnetics to measure from a distance without directly touching an object. Electromagnetic compatibility is another area that's directly involved in electromagnetics. So in this case, they usually test consumer electronics and automotive and aircraft and so forth for lightning strike capabilities. How does you want to make your aircraft and so forth capable of resisting problems when there's a lightning strike. In automotive, you don't want one system interfering with another because it's emitting electromagnetic waves, which happens a lot. Same with consumer electronics. You'll notice on many electronic items that there's an FCC regulation that's been quoted on there and that it's passed some kind of electromagnetic compatibility test. So there's a lot of people that look at electromagnetic compatibility as a career. Optical systems, there's a many number of optical systems around, a lot of them in sensors, a lot of them in medical systems. Fiber optics and communication systems, night vision for military systems. There's FLIR systems, which are forward-looking infrared. Those again are also used in military as well as in consumer devices as well, since they're getting cheaper and more easily accessed. Biomedical systems, there's a lot of electromagnetics that's directly used there. Power systems are more subtly electromagnetic. The transmission lines themselves produce electric and magnetic fields. The generators, photovoltaics, all take advantage of electromagnetics to convert the sun's power into a electric current. And then finally in physics, basic research, radio astronomy, they also deal a lot in medical imaging, etc. So there's a lot of careers in electromagnetics, and there's not that many people that are doing it right now. So it's a very fruitful area to get a degree in and to understand. So if you have any questions or want to know more about electromagnetics or what you can do about electromagnetics or what kind of training you need to have to work in electromagnetics, feel free to reach out.